Let's start with checking the differentiability of a function at a point. In the last video, in the last lecture, we understood what is differentiability and how to check it. So basically we have to apply the formula of coefficient of a derivative. That's what it was, right? What did they tell it? What did they call it? Differential coefficient. We had to find differential coefficient of a function at a point C, and for finding the differential coefficient we had this formula, that is the finding the coefficient, differential coefficient of a function at a point C using the first principles, that was f of c plus h minus f of c upon h when h tends to 0. We have to take the limit of this function. Now, what was C? C was the point at which we were finding the differentiability, at which we were finding whether the function is differentiable or not. So we find the differentiability approaching from the left side towards the function, and then approaching from the right side towards the function, and that is known as left hand differentiability, right hand differentiability, and we check whether the left and right hand differentiability are equal or not. So that's what we have to do in this particular question. The function f of x is mod of x minus 1 plus mod of x minus 2. Weird function, right? Modulus function, and there is addition in between. That's the definition of the function, and we have to check the differentiability of this function at x is equal to 2. So let's first start with the left hand differentiability. So left hand differentiability, or LF dash 2, left hand differentiability at 2, or LF dash 2, they are the same thing, okay? Whatever you want you can write it, is equal to limit of f of c minus h. Notice that in right hand differentiability we had c plus h, but here we have c minus h. So f of c minus h, and what is c? We have to find the differentiability at 2. So c is 2. So 2 minus h, f of 2 minus h, minus f of c, that is f of 2, upon h, sorry, minus h, since this is a left hand differentiability. When h approaches 0, we have to find the limit of this function. Now we know that f of x is equal to mod of x minus 1 plus mod of x minus 2. So what will be f of 2 minus h, and what will be f of 2? So wherever there is x, we have to put 2 minus h, and wherever there is x, we have to put 2 where we are using f of 2. Okay, so how will this look like? It will look like this: limit when h tends to 0 of f of 2 minus h. So this will be mod of 2 minus h, mod of 2 minus h minus 1 plus 2 minus h minus 2 minus f of 2. F of 2 means mod of 2 minus 1. Okay, let's put a bracket here. Mod of 2 minus 1 plus x minus 2. So mod of 2 minus 2, bracket close. This is the whole thing in the numerator, and in the denominator we'll have minus h. We'll not substitute anything in the denominator. We'll first simplify this, and then we'll see that what this function becomes, and then we'll use the formula for function. We know that h tends to 0, so it will be easy to figure out that what is happening with the function. Okay, this will become 2 minus 1, that is 1, mod of 1 minus h. Okay, mod of 1 minus h plus 2 minus 2 is 0, and mod of minus h is nothing but plus h, minus bracket 2 minus 1 is 1 and mod of 1 is 1 plus 0 bracket close upon minus h. So limit h tends to 0 of mod of 1 minus h remains 1 minus h plus h minus 1 upon minus h. So minus h plus h cancel and 1 minus 1 cancel. So we are getting limit of h tends to 0 as 0 upon minus h, which is nothing but 0. So the left hand differentiability at 2, or the left hand uh, derivative is 0. The value of left hand derivative is 0 at point 2. Now let's find the right hand derivative. RHD at 2. At 2 should be written as in subscript, or it can be written as RF-2. Okay, so it will be equal to limit when h tends to 0 of f of c plus h, that is 2 plus h, minus f of c, that is f of 2, the whole upon h. Correct? So wherever there is x, we have to put 2 plus h or 2, depending upon what is the formula of this limit of the function. So limit h tends to 0 of, now see, we have to put in the place of this function, wherever there is x, we have to put 2 plus h first. So f of 2 plus h will become mod of 2 plus h minus 1 plus mod of 2 plus h minus 2 minus f of 2 minus f of 2. Okay, I'll put a bracket here, f of 2. So 2 mod of 2 minus 1, mod of 2 minus 1 plus mod of 2 minus 2, mod close bracket close, the whole upon h. So this becomes limit when h tends to 0 of limit when h tends to 0 of, let's open the mod over here, 2 minus 1 will be 1, 1 plus h will remain as 1 plus h, 2 minus 2 will become 0, 1 plus h minus, let's keep the bracket, 2 minus 1, 2 minus 1 will be 1, 1 plus 0 will be 0. So 2 minus 1 is 1, 1 plus 0 is 1. So this is 1, the whole upon h. Okay, so limit when h tends to 0 of 2h by h, that is limit when h tends to 0 of 2. Now we know that constant limit of a constant number is always the same number. When h tends to 0 doesn't matter, right? So the answer is 2. So what is the left hand limit? It is 0. What is the right hand limit? It is 2. So LF-2 is not equal to RF-2. That means the function is not differentiable at 2. Now see, if you just want to check whether the given function is continuous or not, you can definitely check. It might be continuous. It might be continuous, but it is not necessary that it will be differentiable. Okay, so that is one thing which we have understood in the last lecture, that a function might be continuous, but it may or may not be differentiable at a point in its domain. All right, let's go to the next question. Next question is, find a and b if the function given by f of x is equal to ax square plus b if x is smaller than 1, and f of x is equal to 2x plus 1 if x is greater than or equal to 1, is differentiable at x is equal to 1. Now they have already given that the function is differentiable or derivable at x is equal to 1, and we have to find the values of a and b. Now, one thing we know for sure, that if a given function is differentiable at a given point, then it has to be continuous at that given point. That is the first thing, right? So, if the function is continuous, then its left hand continuity will be equal to right hand continuity. That means the function will be left continuous and right continuous. So with this, what will happen is, if we find the left hand and right hand continuity, we will be able to understand a relationship between A and B. That is, we would be able to find out what is the relationship between A and B. Correct? Let's do that. Okay. So, since f of x is differentiable at x is equal to 1, it must be continuous at x is equal to 1, and therefore we can say that the limit of the function f of x when x approaches 1 from the left side, that is left hand limit, must be equal to the limit of the function when x approaches 1 from the right side, must be equal to the limit of the sorry, not the limit of the function, that must be equal to the value of the function at 1, value of the function at 1. So if we solve this, what do we get? See, when we approach the function, when we approach 1 from the left side, that is from the values which are smaller than 1, the definition of the function becomes ax square plus b when x approaches 1 from the left side. Correct? When we approach the function from the right side, the definition of the function becomes 2x plus 1. So, limit of 2x plus 1 when x approaches 1 from the right side. And when the value of the function, when the value of x becomes 1, the value of function becomes, we just have to substitute x in this definition of the function. Why? Because this is the definition of the function when x is greater than or equal to 1. So 2 ones are 2 plus 1 is 3. Okay, great. Now what? Now, since these things are clear, now let's see what this limit solves and becomes into. Okay, so let's first replace this 1 minus with h tends to 0. Let's solve the limits. So limit when h tends to 0 of, okay, now since we are replacing x raised to 1 minus 2, h tends to 0, in the place of x we will write 1 minus h. Okay, so it will become a bracket 1 minus h the whole square, a bracket 1 minus h the whole square plus b is equal to limit of in the place of, see, this also becomes h tends to 0, in the place of x I'm going to write 1 plus h, so 2 bracket 1 plus h plus 1. Okay, and both the things are equal to 3. Okay, now since h is tending to 0, 1 minus h the whole square will become 1 minus 0 the whole square, that is 1 square, that is nothing but 1. So this whole limit of this particular part will become a plus b is equal to, here since h is tending to 0, and 2 ones are sorry, 1 plus 0 is 1 and 2 ones are 2 plus 1 is 3. So limit of 3 when h tends to 0 is nothing but 3. So we will be left with 2 plus 1, which is 3. So a plus b is equal to 3. That is the first equation we get when we consider that this function is continuous at 1. But that's just one equation. That is just one equation, right? We have to find other equation involving a and b, one more equation involving a and b, so that we can solve these two equations and find the value of a and b. How we do that? So since f is differentiable at 1, since f is differentiable at 1, at x is equal to 1, okay, left hand differentiation at 1 should be equal to right hand differentiation of the function at point 1, which implies that limit h tends to 0 of f of, now see, left hand differentiation, we are approaching uh, 1 from the left side, okay. So what is the formula for left hand differentiation? It is c minus h minus f of c, f of c minus h, 1 minus h minus f of c, the whole upon minus h, right, is equal to limit h tends to 0. Now we are approaching 1 from the right hand side, so it will become f of 1 plus h minus f of 1, the whole upon h, correct, which implies limit h tends to 0 of, now in the place of x, see, when we are approaching 1 from the left hand side, the definition which is going to be considered is this one, and when we are approaching 1 from the left hand side, we'll consider this function, this definition of the function, and in the place of x we are going to put 1 minus h and 1 in the respective terms, okay. So let's do that. So this will become a, sorry, this will become a bracket 1 minus h the whole square plus b minus bracket a bracket 1 square plus b the whole upon minus h. What is minus h? Nothing, just minus h. We have to simplify and find out. And this will be equal to limit when h tends to 0 of f of 1 plus h, f of 1 plus h, okay. Wherever there is h, we have to put, sorry, wherever there is x, we have to put 1 plus h, okay. So a bracket 1 plus h the whole square plus b, let me make some space, a bracket 1 plus h the whole square plus b minus a bracket 1 the whole square plus b the whole upon h, correct. Let's figure it out, what is it, and let's find a relation between a and b. One second, we made a mistake here. The definition of the function will change. Why? Because we are approaching 1 from the right hand side, and for numbers greater than 1 the definition of the function is 2x plus 1. So in 2x plus 1 we have to put this value, so f of 1 plus h, so 2 bracket 1 plus h plus 1 minus bracket 2 bracket 1 plus 1 bracket close. So limit when h tends to 0 of this will become a bracket 1 minus 2h, sorry for this, 1 minus 2h plus h square, right, plus b minus this will become a plus b, so minus a minus b, the whole upon minus h is equal to limit when h tends to 0 of this will become 2 plus 2h plus 1 minus 2 minus 1, the whole upon h minus 2 plus 1 minus 1 all gets cancelled, 2h by h which is 2. Okay, so what does this become? Limit when h tends to 0 of a minus 2ah plus h square plus b minus a minus b plus b minus a plus a gets cancelled, and here is minus h. So this is equal to limit when h tends to 0 of 2h by h, which is nothing but 2. So let's figure it out. Limit of okay, let's take out h common from the numerator, so this will become h bracket h minus 2a the whole upon minus h, correct? So yes. Okay, h minus 2a, everything seems fine. This gets cancelled, this is minus 1, h tends to 0, this is equal to limit of when h tends to 0 of 2. So limit when h tends to 0 of h minus 2a. See, this minus 1 will go up and the signs will change. So this will become 2a minus h and this will become 2. Okay, now h is tending to 0. So limit of 2a minus h when h tends to 0 is nothing but 2a. So 2a is equal to 2. We are getting as 2a is equal to 2 and a is equal to 1. So this implies that 2a is equal to 2, which implies that a is equal to 1. So we already got the value of a. Now what is the value of b? The value of b will be, see, in the first equation, if we put the value of a, that is a plus b is equal to 3. So 1 plus b is equal to 3. Therefore b is equal to 2. Right? So a is equal to 1 and b is equal to 2. These are the answers. These are the values of a and b. Did you understand? I hope you're noting it down, or I hope that you're following the process, the whole method of checking the differentiability, or you can say applying the differentiability and solving the questions. They are easy, but only the process is little long. The applying limits and everything. Slightly long, but yeah, quite fine, no problem. Okay, let's go to the next question. A is 1 and B is 2. Next question is in front of you. Okay, if f is derivable at x is equal to a, if the function f is derivable at x is equal to a, find limit of a function when x approaches a of x multiplied by f of a minus a multiplied by f of x upon x minus a. Okay. Hmm. How will we do this? We have to find the limit of this function. Or maybe we have to just simplify this, whatever we are seeing. But how will we simplify this? See, one thing which they have given to us, which we can use, is f of x is derivable or differentiable at x is equal to a. Hmm. So, if f of x is differentiable at x is equal to a, then we can say that limit when h approaches 0. See, the point at which our function is differentiable is a, that is the c. Okay, so limit when h approaches 0 of f of uh, c plus h, that is a plus h, minus f of c, that is f of a, upon h will be equal to the differential coefficient of the function at point A, or the differentiation of the function or derivation of the function at point A. Okay, so what we have to find? We have to find this, right? See, we know this. This is what the definition of differentiability tells us. That if a function is differentiable at a point, then its derivative is equal to the limit of f of a plus h minus f of a upon h when h tends to 0. Okay, this is the formula. This is the basically definition of the derivative of a function at a point a. Now what we have to find? We have to find limit when x tends to a of x multiplied by f of a minus a multiplied by f of x, the whole upon x minus a. This, the value of this whole thing we have to find. Now first thing which I want to do is I want to convert it from limit of this function when x tends to a into limit of this function when h tends to 0. So whenever I convert from x tends to a to h tends to 0, in the place of x, I'm going to replace x, and in the place of x I have to write uh, a plus h, a plus h. Okay, so let's write that. So this x will become a plus h, right? Because I converted from x tends to a to h tends to 0, this will x will become a plus h multiplied by f of a minus a multiplied by f of, in the place of x I'm going to write a plus h. In the denominator, in the place of x I'm going to write a plus h minus a. Okay, now this will get simplified as limit when h tends to 0 of see, we have a plus h multiplied by f of a. So can we multiply f of a with a and h both? Yes, we can, definitely. So a f of a multiplied by a plus f of a multiplied by h minus, here we cannot do anything, so we'll just write a multiplied by f of a plus h, and in the denominator I will cut a and minus a, and I'm just going to write h. Are you with me here? Just don't lose the touch, okay? Because this is little tricky, but it's not. We have to just go ahead with our regular method, regular concept, and we will get the answer. Okay, now what next? See, now, do you see two terms? I just want to show you over here. You can get confused. So just see this term and just see this term. What is common between these two terms? A is common between these two terms. Can we write them together? Yes, we can. So limit when h tends to 0 of, let's write it as f of a multiplied by h plus, let's take out a common and write it as bracket f of a minus f of a plus h, bracket close, the whole upon h. Now let's separate the denominator and write it as this: limit when h tends to 0 of f of a multiplied by h upon h plus, we can also separate the limits when h tends to 0 of a bracket f of a minus f of a plus h, the whole upon h. Now this h will definitely get cut. So limit when h tends to 0 of f of a will remain as f of a, will remain as f of a. Okay. Now remember what we are trying to find out. Okay, we are trying to find the value of this thing, which is basically the whole thing, which is what we are getting here plus. Okay, what will happen over here? So this will become uh, this will become, see, this a will come out. I think, have we made any mistake in signs? This was this was f of a multiplied by a plus f of a multiplied by h minus a multiplied by f of a plus h. Okay, so okay, I don't think there is any mistake. I don't think there is any mistake. It's okay. It's okay. Okay, there is one thing which I want to show. See, this a is outside the bracket and it is a constant. Okay, because it is derivable at x is equal to a, where a is a, basically it's a real number, so it's a constant. Can we take it out of the limit formula? We can definitely take it out of limit formula. So this becomes limit when h tends to 0 of f of a minus f of a plus h upon h. Does this seem similar, or you can say familiar, this formula? This formula is familiar except the fact that it is exactly equal to this formula where the numerator, that is f of a plus h minus f of a, have swapped their places, as you can see here. So if you write it as f of a minus a multiplied by limit when h tends to 0 of f of a plus h minus f of a, the whole upon h, doesn't make any difference. And what is this thing? Please pay attention here. What is this whole thing equal to? This whole thing, as per the formula, is equal to f dash of a. So f of a minus a multiplied by f dash of a, that is the differential coefficient of the function at point a. So this whole thing is equal to this thing which you had to find the value of, is equal to f of a minus a multiplied by f dash of a. Wow, what a question. Amazing, right? I got confused for a while in between because here the place of f of a and minus f of a plus h was swapped, so I got a little confused. But yeah, it is definitely a very interesting question. Let's go to the next question. Okay, cool. What is this? Examine the derivability or differentiability of f of x, which is equal to x square plus, sorry, x square multiplied by sine of 1 by x when x is not equal to 0, and 0, f of x is 0 when x is equal to 0, at x is equal to 0. Okay, so we have to figure out what is the, whether the function, given function is differentiable or not. Now, this actually does not seem differentiable to me, but we never know actually, because the formula of differentiability is not as, you can say, simple as the formula of limits. That is continuity. Checking continuity is simpler process, but checking differentiability is not. So let's do it. Let's find it out. Okay. So we have this function x square multiplied by sine of 1 by x, where x is not equal to 0. Okay. Now we have to check the differentiability at x is equal to 0. So what is the value of f dash 0? It is equal to limit when h tends to 0 of f of 0 plus h minus f of 0 upon h, which is equal to limit h tends to 0 of, see, we have 0 plus h, that is f of h, so in the place of x we'll put h, so it will become h square multiplied by sine of 1 by h minus f of 0 is nothing but 0 upon h, right? So this becomes limit when h tends to 0 of, see, this h square and this square will cut and we'll get h multiplied by sine 1 by h. Okay, can we simplify this? Can we simplify this? Can we write it as limit when h tends to 0 of h multiplied by limit when h tends to 0 of sine of 1 by h? Correct. Now h is tending to 0, right? So limit of h when h tends to 0 will be 0, and 0 multiplied by anything will be 0, so this will give you the answer 0. Correct. So we can say that at x is equal to 0, at x is equal to 0, the function, the limit of the function when we approach 0 is 0, and at 0 the function acquires the value of 0. So is it differentiable or not? See, if you say that f of x is equal to f dash of x at x is equal to 0, f of x is equal to f dash of x when x is equal to 0, therefore f of x is derivable at x is equal to 0, because the function and its derivative at x is equal to 0, both are same. The value of the function and the value of its derivative at x is equal to, both are 0. Okay, and that's why the function is derivable at x is equal to 0. Not so much convincing even to me, but let's say, one second, let me think about more convincing answer for you. Okay, I just tried the classic way to find the left hand differentiability and the right hand differentiability, and I was able to prove it by that method. So I first found the left hand differentiability, that is LF dash at 0. which was f of c minus h, and c was 0, so f of 0 minus h, which is f of minus h minus f of 0. So wherever there is x, I have to put minus h. So minus h the whole square multiplied by sine of 1 by minus h minus f of 0, that is 0, upon minus h. Right? Now, okay, here I forgot to put minus h. Okay, now in the next step, minus h square becomes h square, sine of 1 upon minus h becomes sine of minus 1 by h upon minus h. Now this h gets cut with this h square, and we get minus sign goes up, and we get minus h multiplied by sine of minus 1 by h. Now sine of minus theta is minus sine theta, right? So minus sign comes outside, multiplies with this minus sign and becomes plus. So limit when h tends to 0 of h multiplied by sine of 1 by h. Now since h is tending towards 0, the whole function, the whole limit of the whole function will become 0. Now we have found out with our earlier method that the right hand differentiability was coming equal to 0. So the left hand differentiability and the right hand differentiability of the function at 0 both are equal, and that is the function is derivable at x is equal to 0. Okay, so that is a better way to prove it. We should stick to our classic methods rather than always following the textbook, right? So yes, so exercise 5b has got around 12 questions, not many. I'm going to give this homework to you now, and this part is finished. Now we have direct differentiation without using the first principles, that is without worrying about the limit. We can directly apply the formulae, and we are going to learn new formulae for of differentiation in class 12th, and we are going to apply them now. More of chain rules and everything is going to come. So yes, so yes, be ready for that, and I'm going to make new video very soon and give it to you. Also, we have to continue with physics, that is capacitor is coming up. It's a big part, big huge video, so both are coming soon to you. Okay, so be prepared for that. Okay, best of luck.